Welcome to Mr. Frolick's physics classes. In this class, we're going to learn the relationship between kinetic energy and work. Hello there. In this lecture, we will see kinetic energy in more details. So we're going to study kinetic energy in more details. Remember, we are representing kinetic energy by Ke. So let's consider this here, that we are in our building. Okay, so this would be our school building. One of you guys is down here, and I'm here. And I will drop a ping pong ball from perhaps the top of the building, third, fourth floor, something like that. And I ask you guys to try to grab it. Would you guys try to grab a ping pong ball that I drop from this height?
I think so.
Yes.
Okay. Now, what if instead of a ping pong ball, I was actually dropping a bowling ball? Would you guys try to grab the bowling ball as it falls?
I would not. But I guess Mark would.
Oh, come on, you're kidding. It's just because he's sleeping. Wake up, Mark, please. Okay, so you wouldn't. And the reason why you would try to grab the ping pong ball, but not try to grab the bowling ball, is because the more massive ball would cause you more damage once it hit down here. So this more massive ball would actually be carrying more energy. Remember, both balls, if we ignore air resistance, would actually be falling with the same speeds. They would arrive at the ground with the same speeds. But the more massive one will cause more damage. If instead of you being here, we just have a sandbox down here, if I just have a sandbox, the ping pong ball would barely cause a depression on the sandbox. But the bowling ball would cause a huge mark in there. So basically what we have then is that the kinetic energy will increase if the mass increases. Since all of our physics so far has been in terms of proportions, I would be tempted to say that kinetic energy will be somehow proportional to mass. But I don't know the power, so I'm just going to say A, where A could be, for example, perhaps 0.5 if it's a root relationship, could be 1 if it's directly proportional, could be 2 if it is quadratic, could be something else, or could be any combination of those. Okay, so we have in here a first relationship for kinetic energy. Now, let's see another situation. If I get a bullet, but I toss it with my hand to some of you guys to hold. So here is the velocity of the bullet after a hand toss. Well, you all could easily catch that bullet. It is a handgun bullet, but if I toss with my hand, you all could easily catch it. But if instead of doing that, I actually put that bullet on the handgun and shoot, bam! Now, none of you guys will try to catch it because that could cause you significantly more damage. The conclusion that we get, of course, is that the kinetic energy will increase as the speed increases. And I would then be tempted to say that kinetic energy is proportional to V raised to a B power, where B could again be somehow 0.5, 1, 2, etc. Okay? If I combine these two equations, I'll get that kinetic energy will be then proportional to somehow m to the a power v to the b power. And remember our lectures on proportion. If that is true, then kinetic energy is going to be equal to some kind of constant m to the a power v to the b power. And so this is roughly what we are looking into. Let's continue our study then. We just saw that the kinetic energy should be a constant m to the a power v to the b power. Now, let's remember, or let's look into units. We saw last class that 1 joule is equal to 1 kilogram meter squared per second squared. Now, what kind of combination of basic quantities of mass and speed could produce this here for me? Okay, you guys are having some trouble. Let me just rewrite this here. I could write this as 1 kilogram meter per second squared. So now please tell me, what combination of mass and speed could produce kilogram meter per second squared?
Mass times speed squared?
Yes, DJ. That's exactly it. Mass here could be given just this kilogram is mass, and meter per second is just speed. So this will become speed squared. And if I bring these ideas in here, then we have that kinetic energy should somehow be a constant multiplied by mass times speed squared. Our task now is to further our studies and try to figure out the value of this constant. Let's see what we're going to get with this. So in order now to move forward and try to identify a suitable value for that constant, I will study the math. I'm going to do some math about the work and change in energy. So I'm going to consider this here. A box that is moving, on my example to the right, under the influence of a constant net force, this way to the right. And because of this, the velocity of that box is increasing. So I'm going to have in here now an initial velocity, and then in here a final velocity greater than the initial velocity. The reason why I'm considering a net force on this system is because the total work done on the object will somehow be equal to that, or should be equal to the change in energy of the system. So the total work will be the work done by the net force. So this is my starting point. And the work done by the net force on that displacement is plus or minus net force times displacement. And because the net force is in the direction of motion, I'm going to stick with the plus. So that it is. Now, this is my equation. In principle, this work here should be equal to the change in energy. Okay? And energy is somehow a constant times mass times speed squared, or at least it should be from what we're talking about. How can I get rid of two things that I have in here that I don't really want to have, net force and displacement, and make somehow A or V show up? Yes.
From Newton's second law, net force equals mass time acceleration.
That's quite of a good idea. You are sharp today. So we would have from Newton's second law that net force equals mass times acceleration. Now, if I get this net force equals mass times acceleration here, and substitute on my equation for work, we'll have then that the work done by the net force on the displacement is going to be mass times acceleration times displacement. Well, by making the substitution of net force equals mass times acceleration, I have mass in here that I was looking for. But now I have a delta x. I don't want those. I need something related to mass and speed. Preference, speed squared. So any suggestions about what I could do here to substitute to make a delta x vanish and some term on speed square show up? Yes.
That v squared equation, the one you told us the story about the police officer. Torricelli's equation.
You got that right, exactly. And the story, you see that the story always is what you guys remember, huh? That's exactly right. If we go through Torricelli's equation, v squared equals v initial squared plus 2a delta x. And then I subtract both sides v initial. So v squared minus v initial squared equals 2a delta x. And I divide both sides by 2. What I have is, on the right-hand side here, a delta x. And on the other side, v final squared minus v initial squared over 2. So if I make now this substitution, my equation will become work done by the net force through a displacement equals to mass multiplied by v final squared minus v initial squared over 2. And if now I apply distributive property in here, let's see what we have. We have that the work done by the net force equals mvf squared over 2 final minus mv initial squared over 2 initial. I guess I said initial twice. But anyways, this is a final quantity, this is an initial quantity. And final minus initial is change. So in one hand, the work done by the net force equals the change on the mv squared over 2. Now, on the other side, we have that kinetic energy is some kind of constant times mv squared. And in here, I have mv squared over 2. So I'm more likely to identify this constant here to be 1/2. And then I can say that kinetic energy, I can define kinetic energy as 1/2 of mv squared. And then, coming back to this side, we can do that the work done by the net force through my displacement equals kinetic energy final minus kinetic energy initial, which we can then write in a more concise way to say that the work done by the net force equals the change in kinetic energy of my object. This is known as work-energy theorem. Notice here, I reasoned with you through an analysis of a conceptual analysis that kinetic energy should be a constant multiplied by mass to the a power, speed to the b power. Then think about units and all of what I had talked before, that work would be change in energy. We kind of inferred then that m should be to the first power, v should be to the second power, so that kinetic energy should be some kind of constant mv squared. Again, if I want this to make sense. Then, by doing some math involving the work done by the net force through a displacement, we got the idea that if I want all of these ideas, all of this here to be consistent, that constant should be 1/2. And then we finally defined kinetic energy as being 1/2 mv squared. So at this point, this is a definition that I'm making with you, or we are making together. I hope you all appreciate this. I hope you enjoyed. And let's now actually move on to solving some exercises involving work and kinetic energy.